that basically deliver both oxygens from the same side, and therefore you end up with a cis 1,2-diol. And like I said, if your solvent is something other than water, then you're going to end up with an OH and an ethoxy group over here. If you're working with a solvent or a reagent like HCl or HBr, you're still going to form hydrogen here, but then it's going to be the halogen that attacks. And we go back to the halohydrin. So from halohydrins, you can form epoxides by putting a base. From the epoxide, you can open it up with HCl, HBr to give you back the halohydrin. This is really cool biosynthesis. Right now they're showing making this manostrol, but from there you can go on to cholesterol. Well, first of all, cholesterol is part of a group of molecules called steroids. This is what we call the steroid nucleus. You have the 5-membered rings in that particular order. The daddy of all steroids are your is cholesterol. You can make from cholesterol vitamin D. You can make all kinds of sex hormones like progesterone and testosterone. You can make adrenal gland hormone type things. You can make all kinds of things from cholesterol. But we make cholesterol from what is essentially an open chain. Right? And here nothing is connected. We're drawing it to get the shapes of the rings, but this is an open chain, but with a lot of double bonds. So the way this reaction starts is an enzyme, squalene epoxidase, this is called squalene. This type of molecule is what we call a terpene. But we make squalene, epoxidase enzyme epoxidizes this double bond right here and make an epoxide right here. Now, from this point on,
it's not showing now.
Wow. I was squinting my head like this.
So now we have something that is electrophilic and can be attacked by a nucleophile. So that's what we're going to have. My nucleophile in here is going to be my pi electrons here that will go ahead and open this up. Now, these pi electrons are going to form a bond right here. But that means I'm going to be left with a positive charge here. So now these pi electrons go ahead and attack that positive charge, form this bond, and leave a positive charge here. So now these pi electrons go ahead and attack here, form this bond, and leave a positive charge here. So now these electrons go ahead and attack and blah, 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 and we form this bond here. So this is a chain reaction, and in one swoop, we formed not just 4 rings from nothing, but 4 rings that have all kinds of specific stereochemistry and chiral carbons in there. So this is a phenomenally elegant way of making this molecule. Then you're going to need to work, a little bit of the detail, but that cyclization, that chain cyclization reaction is just phenomenally interesting. And effective, and again, making all these chiral carbons at once is not trivial. So anyway, that is nucleophile attacking epoxy. Of course, in here it's being enzyme driven, so I don't need to put the strong acid or whatever to open the epoxy. Okay, so it is a lot easier to open up a 3-membered ring epoxide because it's much higher in energy because we have all kinds of angle strain and torsional strains and things like that. This is much higher in energy, so a piece of cake to open it up. Not nearly as easy to open up an ether. They're both ethers, but this is a cyclic ether in a really tiny ring. So because of all the additional strain, it's easy to open up. Okay. Now, like I said, there's 2 ways of opening an epoxide. Right, one of them is liquid acid, and then attack with a nucleophile, whatever that nucleophile happens to be. If it's water, or if it's methanol, or whatnot, right? And now let's make this unsymmetrical. So, because this is a more substituted carbon, yeah, so I don't need to know the other one. So, because this is a more substituted carbon, this epoxide is unsymmetrical and it's actually more positive charge here. So your nucleophile will attack the carbon with the most positive charge. This is going to open up, and I'm going to end up with this facing forward. And because this is an SN2 reaction, we have an inversion. Right? So, since this methyl was, well, the methyl was on the back and this was facing to the front, this does a backside attack opposite to this. This is now going to be on the back, and this is going to be in front. Eventually, there's like an additional step where we lose this hydrogen and we're left with OH. Okay? And if this had been methanol, then we would attack here, we would lose this, and you would end up with OCH3 here. That's under acidic conditions. Now, if you were under basic conditions, so let's say I put sodium hydroxide. Now, there is no carbon that has more positive charge for my nucleophile will be attracted. The only difference here is the fact that this end is less sterically crowded and this is more sterically crowded. So at this point in time, my hydroxide will just come to the less sterically crowded end, open this up from the back, I'm not changing the stereochemistry here, but I am inverting the stereochemistry here. This is coming from the back. And so we're going to end up with that. So, or if you were coming with, let's say, sodium methoxide, you would have OCH3 here. Look at the difference. In here, we have OCH3 and methyl on the same carbon, and here we have OCH3 and methyl on opposite carbons, because I'm attacking a different carbon. And here, In here, I'm attacking the carbon with the methyl group. In here, I'm attacking the carbon that doesn't have the methyl group. So that's how you end up with these different products. You're still going to have your trans 1,2 diol, but different groups are going to be in different partners. If you come with water, you can't tell the difference. Because OH is OH is OH. But if you come with another solvent, then you're going to be able to tell the difference.
Oh, I'm sorry, could you explain one thing? On that same slide you just had, why on the basic condition attacks the less stable carbon?
It's not less stable, it is less sterically crowded. This takes space and it's kind of blocking this OH from approaching from this side, whereas this with a hydrogen is more open, so it's easier for the OH to approach from the less sterically crowded.
But what about the top one now?
Well, in the top one, we have another factor operating here, which is the fact that, if I draw this kind of like this, okay? Majority of my positive charge is on this end. And so, because this has a positive charge, which this doesn't, it is the more substituted carbon that can better bear that positive charge.
Gotcha, now
And that's why this approach is from this end.
I didn't see that had a charge. I thought it was
That's what this is doing for you.
right.
It's adding that charge over there. Okay. So, now, you can use any kind of nucleophile to open those epoxides. It doesn't need to be OH or methoxide. You can put cyanide or azide or a thiol, whatever, thiolate ion, ammonia, whatever. There's all kinds of ways of opening that epoxide. All right. So let's look in here. So if you have just plain ethylene oxide, okay, nothing else, no groups in here, no nothing that I need to worry about, and I'm using sodium methoxide to open it up. Let's then toss it into some acidic water. So show me the products that you formed. Why am I putting the acidic water later?
Because the oxygen has a negative charge. Right. So
So let's say we did this first. So my methoxide ion, my nucleophile, goes ahead and attacks, opens this up. So the first thing I'm going to form is this alkoxide ion, right? And then once I toss it in some acidic water, this is going to pick up a hydrogen, and I'm going to end up, let's say, with that. So what are the other two products? from my cyanide ion. I'm gonna add here, open this up, and I'm gonna end up with this carbon connected to this carbon, and connected to this carbon. And the same with the amide, NH2 minus, this attacks, opens up, and we're going to end up with that. What other nucleophile did we look at before to extend the carbon chain? To make a carbon-carbon bond? Grignard, right? So you could come in with a Grignard, whatever. And attack, and open up, and then we would add, let's say, CH2, CH3, connected to my CH2, CH2, but that was a way of getting two carbons between whatever was coming from the alkyl halide and the OH. Okay, so again, we just covered this, the regiochemistry of which carbon of the epoxide will the nucleophile attack. So you're coming with an epoxide ion basic condition, we're going to attack the least substituted carbon. If this was in the presence of acid, where we're putting a positive charge on a more substituted carbon, that is the carbon that this is going to attack. Eventually we'll use hydrogen and attack the opposite. Now, like we said, Grignards can open epoxides, like ethylene oxide, can give you alcohols, nothing new about that. So, let's look at an exercise with that. So, I have one hexene. And first I want to convert that. I'm not showing any stereochemistry here. And then from one hexene, I want to form one methoxy to ethanol. And then from one hexene, I want to make two methoxy. One hexanol. So what are the reaction conditions that I need to get each of these? What's the first step that I'm going to do? How am I adding this stuff to what?
So PR.
What am I opening with, let's say, methoxide to give me an OH here? From the same starting material, first, I'm going to form the epoxy, let's say methacrylic peroxybenzoic acid or some other peroxybenzoic acid or some other peroxy acid to give me this. And then I can open up the epoxide, right? So the question is, do I open from this carbon to give an OH here, that would be this case, or do I open from this carbon to give the OCH3 here, right? I'm opening from different carbons. So, what type of reagent, under what conditions am I to do that? Acidic or basic?
Basic.
Basic, right? I'm coming to the least substituted carbon under basic conditions. So, basic conditions would certainly be methoxide ion. I don't put it as methoxide, let's say sodium methoxide, something like that. I add that first, then toss the whole thing in water, that will give me that. What basic conditions do I have in here? Do I have a Grignard, right? If I'm going to be making a carbon-carbon bond, chances are I'm using a Grignard. Grignards are, of course, powerful nucleophiles and powerful bases. These are basic conditions, right? So I'm going to add a Grignard, let it open, end up with the epoxide ion, toss the whole thing into some water, and then I have the alcohol. Okay, but both of these are in the basic conditions to open the least substituted carbon, to attack the least substituted carbon. To attack the more substituted carbon, I need to be under acidic conditions. So I'm going to have acid, sulfuric, something like that, and now methanol. So the acid, the oxygen protonates, then the methanol comes and opens, then we lose this hydrogen, and we end up with this product. Why would I not use an acid like HCl? Because the chlorides could end up adding. Chances are not, because I'm going to have a lot more of this, but why mess around? Okay, so this is under acidic conditions, which ends up with a different regiochemistry. To which region of the molecule does the nucleophile attack? This is attacking carbon number 1, this is attacking carbon number 1, this is attacking carbon number 2. 1, 2, 1, 2. don't worry about, we do nothing with plastic, so anything that will tell you on polymers and plastics, of course it's a phenomenally important part, but we just don't have time to get into this, and I can talk semester worth of plastics, or a year or more. So, but anyway, so let's finish with some problems here. So we're going to do some synthesis. So what's the first thing that your carbons, the starting material and then my product. I have 3 carbons here, and that's the only starting material that I can use. So clearly, I'm putting 2 3-carbon pieces together by making this bond. That makes sense? I need to make a carbon-carbon bond. How do we make carbon-carbon bond?
Good.
Good. Okay, so thinking backwards in a retrosynthetic analysis, I could make a carbon-carbon bond.
Thank you.
I need something here with a leading group, and let's say this is my gradient. What kind of leading group could I have in here? That we've been studying like that.
VR.
Why? Because I need something here that I can then change to a bromine. And I can change an OH to a bromine. Right. So my Grignard attacks here gives me the alcohol, and then I just change it to a bromine. Okay. But the key is recognize the pieces, recognize the bonds that you make, recognize what the strategy is at Grignard, and then the rest are details. Okay? So, now, I need to then, from here, make this Grignard, and from here, make this epoxide. The epoxide should be easy, right? How do I make epoxide? NCPVA. Let's try to be somewhat consistent. So NCPVA. NCPVA. That would give me that epoxide. How about the Grignard? What do I make Grignards from? Can I make a halide from an alkene? Yes. How can I make it? Bicarbonate or antimicrobic, HBr or HBr with peroxide. Do I need bicarbonate or antimicrobic? Really? Antimicrobic is here. I need to make here. That's bicarbonate. Okay. So I add HBr. If you did, and then I add magnesium and make it great. Right? So when I write this forward, I start with my starting material, I add magnesium, I then add the epoxide that I made before, and it's waiting for me, and I acidify, and that will give me this. And then I put some HBr, I'm sorry, PBr3 because it's a secondary carbon. HBr, they were like a tertiary, but let's say PBr3. And that would get you that product.
Right, for each phosphorus.
I could put calcium chloride and then some sort of sodium bromide or something like that. Yes, it's just that.
So on an exam, is this how like you want us to show? Like, do you want us to show like the HBr going first to form like the BR?
Oh,
No.
Never mind.
Okay.
Yes. That was the whole point. You need a halide to make the group.
So if we wanted anti-Markovnikov, it would be HBr and peroxide.
Making recycled halides is important because we need them to make radiants. Okay. But it's imperative that you come up with a plan. That you look at what you have to work with and what is the product. And what are we going to connect to what? Okay. But once you have a plan, then you know, the rest is details. What's my plan?
Oh, yes, green.
But what's the problem here? Can I make a Grignard? What happens if I put this Grignard in this alcohol? The Grignard acts as a base and kills my alcohol. So I'm going to need to be a little bit more inventive. We know that the ways to make alcohols could be from epoxides, right? So if I had an epoxide like this, and in my Grignard attacked this carbon, no, that's not the carbon we want to attack.
The top one. The top
Okay,
one.
so
Yeah.
attack this carbon and, no. How do I get DOH? Oh,
That we pull it over.
Oh. Oh. That would leave me there originally. So, the question is, I know how to make a Grignard from it, that's the reason. How do I make an epoxide from this? What do we make epoxides from? Alkenes. Can I make an alkene from an alcohol?
Yes.
Dehydrate, right?
That's just-
Let's put some acid, cook it, and we eliminate. And then we make the epoxide. Now we're ready to go. down. I will put bromobenzene. And first I add the magnesium and ether, and second I add the oxide, and third I put a little bit of acid, and there we have the product. Again, these three carbons are clearly giving you this. And we need to join these two, and of course a carbon-carbon bond you're thinking in terms of agreement. So this is a little bit tricky because, hey, it's not as simple as just adding these two together. You get that? Synthesis requires practice. You need to know your reactions to be able to do any synthesis, but then you need the more global view of it. What do I have? What do I end up with? Which are the bonds that I'm making? What is the strategy to make those bonds? Okay. And to make a bond, I need a leading group. How do I make this into a leading group? But you need the big strategy. All right, we're done with all the material for the first exam, which is not going to be until a week from today, because we need to do all the physics. We start today with the quizzes at 2 o'clock in this classroom, then Tuesday at 2 o'clock in this classroom, then Wednesday in the morning and Thursday. Okay. Anything else that I said today is not going to be part of the exam. The exam is only chapters 10, 11, and 14. So let me start with chapter 12. Okay. It's not going to be on the exam.
I just have a question about the exam. Is it like free responses like your class problem? Okay. But the quiz will be multiple choice.
The quiz is multiple choice just simply because there's only so much grading I think. But the exams which are credit, absolutely.
Okay.
So you're going to have in your exam, obviously some naming, some reactions where you're going to need to tell me what's the product of this reaction, what is the reagent of this reaction, what is the starting material, and then you're going to have some more synthesis, some of them guided, fill in these blanks in this sequence, some of them more open-ended like what we've been doing now. So pretty much just like the class problems have been doing.
And you come on naming starting from chapter 10, 11, and 14.
No, the naming will be about alcohols, ethers, epoxides, thiols. All right. Now, chapters 12 and 13 are totally different. And then we go back to looking at functional groups and their chemistry, how do you make them, how do you reactions of them, synthesis. But 12 and 13 deal with spectroscopy. IR, NMR, proton, carbon, GC, mass spec, whatever. Why is that important? Because we don't have this type of vision that actually sees this molecules. So unless I can see somehow what I'm dealing with and light, the way to see molecules is through spectroscopy. Irradiate those molecules with different frequencies or wavelengths of light, and you will see different absorptions of different frequencies or wavelengths of light. Depending on the absorption, you can identify different bonds, you can identify, all kinds of things. So between all of these different techniques, we can uniquely identify, this mystery liquid that we have in here. The sort of ultimate answer would be to do X-ray crystallography, because that literally maps out all the electrons in every atom and uses those electron densities to give you a three-dimensional picture of the molecule. But A, you need a crystal, you need a solid, you need a very good crystal, and it's a very expensive technique. Not everybody has the ability to do X-ray crystallography in every single molecule that you're looking at. The others, IR and MR, are a lot more daily occurrence. Any lab anywhere has an IR, has an NMR. And that allows you to quickly follow your reaction and see what's happening. Okay. So, we're going to start with IR. In general, let's note that this will be. What information are you going to get from each technique? So, infrared looks at functional groups. Infrared can tell you, oh, you've got a ketone there. You've got a carboxylic acid. You've got a nitron. It's very good at identifying functional groups, but not your carbon backbone. It cannot tell you that you have a 6-carbon nitron. It will tell you there's a nitron somewhere there, but what is it attached to? I don't have a clue. Mass spec, we're going to do very little of it. Your typical organic chemist, and that's what I am, so that's how I've been trained, uses these two techniques as sort of your workhorse. I want to look at what the heck I have here. Those two are going to give me 99+% of the time the information that I need to identify a compound. Now, if you want to really get some more details, mass spec does provide one useful piece of information, and that's the molecular weight, the molar mass of that compound. That can be interesting. But short of that, what mass spec does is it explodes a molecule into tiny fragments. And then you're playing the game of trying to figure out where these fragments belong in this molecule. It's kind of not very efficient, and you can get the same information so much faster from one of those two techniques. So we're not going to bother with that. UV is interesting not because of identifying molecules, because not very many molecules absorb UV. You need to have a conjugated set of double bonds like in a benzene ring to absorb UV. But it's interesting from the perspective of, let's say, biochemistry or something like that, in that it allows you to follow amino acids, small peptides, whatever, that have those UV active groups. Because most of them don't. So you can sort of focus on those that do have that UV active center and follow, well, this has that. This doesn't. Or this is converted to this, and I can follow that by UV. Okay. But we are going to spend minimal amount of time on mass spec and UV, and lots of time, well, some time on IR and lots of time on NMR. Okay. So NMR gives you your carbon, hydrogen framework. this is what's going to nail. Oh, you have a nitron here, and that nitron is connected to 6 carbons in hexane nitron. Okay? So NMR gives you that carbon-carbon-carbon-hydrogen backbone. So they provide different informations, and then you put both of them together, and you come up with a bond. All right. Now, let's go back to the basics here. Spectroscopy means you're irradiating your sample with light, different frequencies, different wavelengths of light. So what was the frequency of the wavelength? The red light travels in waves. The length, the distance between 2 wave crests is your wavelength. We measure that in centimeters, nanometers, it's a distance, sometimes angstroms. If I stand here and I watch how many cycles go by me per second, let's say this is 1 second, okay? So I had 3 cycles per second, right? That is a frequency. So 3 cycles per second, I can also say 3 hertz, or 3 hertz, okay? That is a unit that we use for frequency.
You can tell the cycles by just looking at the peak.
Well, you can't see. You can see the wave. I have a forecast of waves that are traveling here, but I can't see that. But your spectrometer can. Your eyes cannot, right? But the spectrometer can. So, when you're listening to the radio or whatever, 93.1 megahertz or whatever, that's what they tell you. The frequency of which that radio station is emitting is different. All right, so you have in your spectrum different frequencies and wavelengths, right? So in here we're going from a very long wavelength to a very short wavelength, right? Where the peaks are very close together. If you have very long wavelengths, you have very low frequencies. So, let me just draw this. An artist I'm not. But, so, this is a longer wavelength. We use this Greek letter lambda to indicate wavelength. Right? So my wavelength is long. My wavelength is shorter. But in here, my frequency is, let's say, 2 hertz. While my frequency here, we consider this is 1 second and this is 1 second, is 4 hertz. So this is higher, this is lower. So wavelength and frequency are inversely proportional. We know that the product of the two equals the speed of light, right? But regardless, they are inversely proportional. One is long, the other one is short, or vice versa. So in here we have long wavelength and short wavelength and high frequency and low frequency. Okay? Frequency is directly proportional to energy. So this has high energy and this has low energy. Okay? So when we start here, this is 1 meter. That's a huge wavelength. Okay, very low energy. We're talking about radio waves and TV waves. Very low energy type of waves. A little bit, and this is talking about the wavelength and how broad it is. So this is about, the width of a human. This is the width of a fingernail, pinhead, dust, bacteria, you can't see bacteria, so we're starting to really get small as far as the wavelength is concerned. But anyway, microwaves, infrared, okay, shorter wavelength, increasing energy. Inserted in here is your visible spectrum, which is expanded in here. We cannot see any of the others, only the visible. And then beyond the visible goes UV and X-rays and gamma rays. Now we're starting to get to really damaging, very high energy type of rays. Somewhere in here, we have sort of like the threshold past which we start causing what we call biological damage, right? Breaking bonds in DNA, stuff like that, causing mutations, cancers, blah, 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 blah. Okay. So, we're going to be studying irradiating molecules with IR. That is not strong enough to break bonds. It is strong enough to make these bonds stretch and bend, but not break. UV, on the other hand, can and will break bonds. NMR, we're using radio waves. This is the weakest type of radiation that we can expose something to. This does not cause breakage, does not cause bending or stretching, but it does affect the protons in the nucleus. And it makes them just a spin flip rather than spinning like this, spin and spin like that. Okay, just a little change in their motion. Okay? And that we can measure. Alright. So, different techniques that use different strength of radiation and cause different absorptions and analysis for that. So we're going to start with IR. Okay. Well, this is telling you what you do. Blah, blah, blah. So, in IR, so we talked about your wavelength, which is in some unit, like centimeters or micrometers or whatever. We talked about the frequency in units of hertz or cycles per second. Let me talk about something which is, so frequency and wavelength are inversely proportional. Now, I'm going to come up with something called a wave number, in which I'm doing the reciprocal of the wavelength. Your wave number is kind of sort of like a frequency. It is inversely proportional to your wavelength. It's not exactly a frequency, but this is what we use when we talk about IR. So in a way, you're talking about, and if this is, let's say, in centimeters, then your wave number is going to be in reciprocal centimeters. If this is in meters, then it's in reciprocal meters, or whatever. Okay? But they're inversely proportional, your wave numbers and your wavelengths. All right. In IR, you're going to be looking at a spectrum that will go from about 4,000 reciprocal centimeters to, what? 600, 0, whatever you want. Okay. So, which one is higher in energy? The left-hand side or the right-hand side?
The right hand side.
The left. Because think about frequency. Higher frequency is higher energy, right? So higher wave numbers is higher energy, all right? So what I do is I put a sample in my IR machine, and I irradiate it with changing frequencies of wave numbers. And as I hit my different wave numbers, some of these things, I have a baseline, and we absorb. Right? Oh, I absorb. oh, I absorb, okay? And so depending on the wave number, different functional groups will absorb at different frequencies at different wave numbers. And based on that, I can tell you what the functional group is, okay? Now, in a very generic analysis, so this is what an IR spectrum actually looks like. Right? From about 600 to about 4,000, higher energy radiation, blah, blah, blah. The area up to about 1,400. This is when my single bonds between heteroatoms, not hydrogen, but carbon, 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 oxygen, carbon, nitrogen, absorb. Somewhere in that window. There's 8 gazillion carbon bond in any molecule, which means I'm going to have 8 gazillion absorption peaks. I'm not going to look. I can't get any useful information out of that because there's all kinds of overlapping peaks. So I call this the fingerprint region. And I don't even bother to look at that. So when I look at something like this, I say, well, you know, ignore that. That's a lot of noise that I'm not looking at. So basically now I'm looking here and here. Now, we're going to learn that these sharp, fairly strong peaks right at about 2200 correspond to a nitrile, because this is where my triple bonds absorb. And there's only 2 triple bonds, a carbon triple bond nitrogen or a carbon triple bond nitrogen. Your carbon triple bond carbon typically is smaller and will absorb, if this is 2200, your carbon triple bond will typically absorb at a little bit less than 2200, while your nitrile will be sharper, deeper, and absorb a little bit above 2200. Depending on the molecule, but that's where your carbon triple bond carbon comes. Your carbon double bond oxygen, carbon double bond nitrogen, carbon double bond carbon absorb in this area. Now, carbon double bond oxygen is your strongest peak always. If you have a carbon double bond oxygen in there, you cannot miss it, okay? It's going to be a beast like that, and you'd be blind if you don't see it, okay? If you've got a carbonyl, you will see it, all right? And there's no mistake in a carbonyl, a carbon double bond oxygen. Now, that carbon double bond oxygen will be an aldehyde, a ketone, a carboxylic acid, an ester, an amide, and we're going to see the difference in how those peaks move and, you know, other stuff. But that carbon double bond oxygen, you will see, okay? Now, your carbon, and for ketones and aldehydes, that's going to come closer to that 1700, while a carbon-carbon double bond will come more like 1650, maybe 1620. So you can really tell the difference. You know, here's your carbon-carbon double bond. Here's your carbonyl. Okay. Different pieces.
So is this showing how much light it absorbs, or to stretch the bond energy?
It is, yeah, it is a stronger absorption based on polarity and things like that. Okay. So I don't really have time to get into all the nitty gritty here. We'll do that on Tuesday. But that's the general idea of IRS. It identifies functional groups and we'll be able to establish them. Okay, so let's just quit here and continue. You have certain carbons that will give me a second. There's so few carbon that will nitrogen, what we call amine type. Or the triple bond, the nitrile. Yeah, this is your nitrile, and this is your carbon. One thing I forgot to mention is this area looks at single bonds between hydrogen and carbon, or hydrogen and oxygen, or hydrogen and nitrogen. Okay? NH and OH can hydrogen bond. So these are peaks that I'm going to show you. Big, because a hydrogen bond is constantly changing between any two molecules, whether you get closer or further away. So it's not a single absorption, but a huge, massive peak. Whereas your carbon-hydrogen bonds tend to be sharper. But it depends on whether you have an sp3 carbon attached to a hydrogen, or whether you have an sp2 carbon attached to a hydrogen, or whether you have an sp carbon attached to a hydrogen. You can clearly tell them apart. So right now, what I can tell you from this molecule is it's saturated. I only have sp3 carbons, and it's got a nitrile. That's it. That's all the information I can tell from that one. Okay? Alright, now we're gonna read it.
Except, will the pop quiz answers be up on Wednesday afternoon or Wednesday?
So the deadline to take this is Wednesday at around 10:30, whatever. After that, I will post the answers in the class. Okay?